Drift transport. Drift transport means that the carriers are going to move in an electrical field. So that the electron is going to move against the field. This is the velocity of the electron. And the hole is going to move with positive charge in favor of the electrical field. Then the current is the charge, the electrical charge, times the flux, and is the product of the electrical charge, the concentration, the mobility, and the electrical field. So that the current for an electron will be the charge, the density of electrons, the mobility of electrons, and the value of the electrical field. This will be the current. Another important quantity is the conductivity. This is the product of the electrical charge, the density, and the mobility, so that the electron current is going to be the mobility times the electrical field. For holes, we have similar expressions. And also the conductivity is the hole density and the hole mobility. Note that the current goes in the same direction, so that for both electrons and holes we have the current in the direction of the electrical field. So now we consider a material with two contacts. One contact here. So here is the Fermi level of the electrons. The density of electrons is constant in this device. So when we apply a voltage, we are going to have a flow of current by the drift in the field. So this is the situation by applying a negative bias to the left. And now we're going to have the electrons going downward in energy. And the electron current will be, the electrical current will be to the left, opposite to the displacement. So if we have holes moving in the valence band, they go upwards in the tilted energy diagram, and the current is the same direction. So now we can analyze a device where we add two contacts with different work function. And we then this will come to equilibrium. And it has a built-in voltage, which is just the amount of the field. So here the contacts play no role in taking the built-in voltage. Everything is invested in a field, and this is like a capacitor because there is no space charge inside. the possible inside density makes no effect in the electrical field, all the charge will be at the contact. So now we can change the bias, and now by applying a bias voltage, we can change the tilt of the bands. For example, if we apply just the built-in voltage, we are going to bring to the flat band position. And if we apply a higher voltage, then this is probably going to inject charge, because here is easy to come in and then the charge will go out. And this is the forward bias. On the other hand, we can apply a bias in the other direction, and this is the reverse bias. So we can modulate the direction of the electrical field, and if there is photogenerated charge, we can control the direction where the charge is extracted. This is one example of a very thin bilayer solar cell that is obtaining electrons and holes, and the electrons simply go down in the electrical field until they are extracted at the cathode. Therefore, this solar cell will operate by the direction of the electrical field. However, this is not really the normal situation in very efficient solar cells, because efficient solar cells normally have a large collection region and work by a small diffusion force to extract the charge. There is another important situation in which the injected carrier density has an important effect on the electrical field. In this mechanism, the carrier density is creating an electrical field, and this electrical field is moving the charge so that they are coupled, and this is called space charge limited current. To find the distribution of carriers and electrical field in the space charge limited current regime, we need to solve two combined equations. The first is the equation of the electrical current, which contains the product of the electron density and the electrical field. And the second is the Poisson equation that relates the derivative of the electrical field to the amount of local charge. An additional important equation is that the current is spatially continuous, so that when the charge density is large, the electrical field is small. And we are going to solve this equation assuming that the injection at the cathode is at zero electrical field. So that is this point. Then by solving the differential equation, we obtain the dependence of the electrical field on the position, and we can also find the carrier density since the current is constant. And this is the dependence where the carrier density is maximum at the beginning and decreases while the electrical field is increasing as a function of the distance, so that the product of both is constant. If we write the equation for the current in terms of the electrical potential, then we have this characteristic dependence of the Mott-Gorney law, which is dependent on the potential to the square and inversely proportional to the third power of the thickness. And this can be investigated by varying the thickness of the samples to check that you are observing the space charge limited current. So then the square root of the current must be proportional to the voltage, and this is the case observed in the measurements. However, when there is trap limited transport with a lot of traps, the traps modify the distribution of the electrical field, and then we have a more general power law than just the square. There are additional dependencies indicating that there is a distribution of traps in the sample.